network time protocol says it's 12:19. Verizon says it's 12:16. What time do you all think it is?
My Verizon says it's 12:19.
My Verizon time protocol says it's 12:19.
That's weird. So my phone was 3 or 4 minutes off the other day, so I rebooted it thinking it was my phone's problem. It's still 4 minutes slow. Time for a new phone. And
What's the issue?
it should set. I mean, my phone should set off the network, and the cell tower is good to the nearest nanosecond because it's phase locked to GPS. So I don't know. So you all of course know that tomorrow, Sunday is Nano Day in the U.S.
Yeah.
10/9, 10 to the minus 9. Man, is that geekly. I sat out on the monitors at the end of the hall this morning. That's the only reason I ever heard of it. So, let me remind you, there's no class on Monday. I think you all know that. The lab will be open from 3 to 6 Monday afternoon, courtesy of Andrew, and be open from 10 to 4:30 on Tuesday. And you can check out on lab 3 anytime during on Tuesday. The Tuesday group can also check out on Wednesday up until Wednesday evening, until 7:30. Now, given that there's 2 lab sections they're going to check out at the same time, at least potentially, Wednesday and Tuesday, there is going to be a sign up as soon as you get into the lab for demo slots. So get the TA to give you the demo slots as soon as possible after you get into the lab on Wednesday. Oh yes, Wednesday, I think last time the feeling was that since there's a big deadline for approximately half the class by Wednesday night, that your ability to absorb anything in a lecture would be low, and therefore we should have lecture in the lab. In other words, it should just be extended lab hours on Wednesday. Do people still feel that way? Or would you rather have a... What?
What's the deadline?
Lab 3. Wednesday.
Class, not another class. Okay.
I don't know about other. Well, I know that there's a big deadline. I think there's a test on Thursday, right, in Compark, that some people are beginning to already hyperventilate over.
Oh, don't worry.
Just don't worry. Yeah, it's fine. But what do you think? Lecture next week. So the trade-off is we don't have a lecture, then the material gets pushed back 1/3 of a week. We do have a lecture, you can't work on the lab. What's the feeling here? Anybody have an opinion? Yes? More lab time. Second. At least somebody has an opinion. That's nice.
I kind of want lecture.
You kind of want lecture. That's a first. Okay, so let's go with lab for Wednesday, and then we'll. But that means we have to do some lecturing today. The sort of trade-off was, well, the day before a big break, there's not too many, but there's a fair number of people here, so that's okay. Any questions on lab 3? I've seen some strange things the last few days. One was trying to define what I meant by drag. And if you remember from the lab write-up, there's, after you compute the momentum transfer between the balls, then there's a update of the of the velocities, which you will notice takes the form of a Euler integration of a first-order differential equation. In other words, it exponentially decays the velocity as long as the drag is small. And so this drag is a per frame drag. It is not per collision, and it is not per wall collision. It is per frame. In other words, you should model it in your head as if it's like rolling friction against the table these balls are all on. The collisions are frictionless and lossless, both with the walls and between balls. One thing this does, a small drag helps overcome numerical instabilities. If you have round-off errors that result in non-conservation of energy, which is easy to do in a finite system like this, then adding a little bit of drag stabilizes things by dissipating a little bit of the excess energy that you don't conserve every time, makes it less obvious there's a numerical error. That's why I almost always put drag in numerical stuff, because it stabilizes it. One student came up with the observation that well, I said, first of all, that r equals 2 is a nice radius, because 2 times the radius squared is equal to a power of 2. In this case, 16. What other radii have this nice feature? That's what the student came up with. What other radii, which when multiplied by 2 and squared end up being a power of 2? 1. What else? 4. So those are all really good impact radii for balls for this simulation. I suggested 2. You could use 1. Using 1 might be nice if you manage to animate, say, 10 to the third balls. Then it would get rather crowded if they were of radius 2, but you might be able to fit in radius 1 balls.
Bruce,
Yes?
for the fixed time thread to ensure the frame rate,
Yes?
why was that preferable to doing an interrupt service routine?
Why is it preferable to have a timed thread rather than an interrupt service routine? So in this case, given that the compute load is so heavy, there's no particular reason why it's preferable. It takes a little while to get into an interrupt service routine, it takes a little while to get out, but for some giant calculation like all these ball interactions, it's not clear that it matters. If you were using a preemptive threader, then it would be nicer to run in a thread because you could preempt for keystrokes. Given that this threader is not preemptive, there's no strong reason not to run an interrupt service routine. You do have to run at least one other thread which ticks out seconds. But you could still do that with an ISR. That's a good question. Yeah, there's no strong reason not to put it in an ISR in this case. You do not, however, want to have any ISR running for the sound production. None. Oh yes, pixels per frame. I've seen people do the weirdest thing with velocity units here. I specified in the lab that a reasonable starting velocity might be minus 30 to minus 60 pixels per second. Well, you know, if you're going to go at a frame rate of 15, then that's something like 2 to 4, minus 2 to minus 4 pixels per frame. No reason to not use frame time as a DT of 1. You want to eliminate as many multiplies as possible. Multiplies are expensive when you're doing a fixed multiply. So if you can make the DT in these equations up here, if you can make the DT equal to 1, you avoid a multiply. One way to do that is to say the time unit is 1 frame. Then the units of motion are pixels per frame, and with the distance measurement in pixels. Don't make it any more complicated than you have to. Any other? Yeah.
You mentioned setting the clock to maximize the SPI transfer rate.
Yes.
Talk a little bit more about that.
Setting the clock to maximize SPI transfer rate. The documentation on setting SPI divider is cryptic. And it's a several bit field, and I couldn't decide by reading it whether you can set the SPI clock divider to, you can certainly set it to 1, you can set it to 2, you could set it to 4. I couldn't tell by reading the documentation whether you could set it to 3 or not. Experimentation shows that doesn't work. At least not in my hands. Has anybody else tried it? You guys are smiling like you tried it, but okay.
We're smiling that this 3 doesn't work.
Right. So they're doing 1-bit coding is what it amounts to. It's not reading it as a number. It's reading it as a 1-bit pattern. So the maximum speed you can run the interface to the TFT is about 20 megahertz. Might be a little faster, but not much. That's limited by 2 things. One is the internal processor on the TFT, and the other is the very significant capacitance on the whiteboards. Every pin on the whiteboard is coupled to the pins next to it by something like 10 picofarads. You start calculating rise times on a 20 megahertz waveform, and a very few ohms wreck your rise time. And you can see that if you look at the clock at 20 megahertz on a scope. It doesn't look like this. It looks more like that. It's very degraded. It's amazing it works at all at 20 megahertz on the whiteboard. So, for a couple of reasons, you can't go faster than that. So, given that you are limited to dividers of 2 and 4, let's see, what could you do? You could set the CPU to 40. So this is the CPU. You could set the PB bus to 20 and the SPI divider to 1. Or you could set the core to 40, the PB bus to 40, and the SPI divider to 2. Let's say that you want to get maximum CPU speed. What's the fastest anybody's tried to overclock it so far? You haven't tried to overclock it? I'm so disappointed. Nobody's tried to overclock? Anybody tried to set it to 60? Wow, what a conservative group of people. Very nice. So you could set it to 48 megahertz, then divide by 2 gives you 24. That's too fast. Divide by 4 gives you 12. That's slower than you want to go. If you set it to 60, set the core to 60, and set the PB to what? Let's set the peripheral bus to 60, then to get maximum SPI rate, we have to divide by 3. We can't do that, so we have to divide by 4, and we get 15 megahertz. Does that matter? It depends. And what it depends upon is the relative amount of time that it takes to do the numerical calculations versus the SPI transfer to draw a ball. That in turn is determined by how many points you put on the ball. So, you draw a ball with 1 point, it's going to take 1/5 the transfers if you draw a ball with 4 points. If you change the color of every ball, it's going to add at least 1 SPI transfer per ball. So, I believe that the minimum number of transfers to do one ball is right around 4 SPI transactions. So it takes something like 4 microseconds or so. It actually takes about 5 microseconds to draw a ball, draw 1 point. So is that faster? That's it. 20 megahertz. So 20 megahertz SPI rate. So does it take longer than that to do a calculation, or less time than do that to do a calculation? I don't actually know. I'm guessing that the SPI is slower. I haven't actually checked it. I'm guessing that the SPI is slower because I'm kind of adding up the number of cycles it takes to do one ball, and it sounds like 5 times 50 cycles is more than it's going to take to do the calculation, but I'm not sure. So the result is that you should probably, I'm saying probably optimize for SPI rate. I'm SPI rate. The I rate, it's how you parse it, right? The SPI rate, sorry. It's stupid jokes, yeah. So it's probably the case that the SPI rate is going to be more important than the CPU rate. But I don't know for sure. So now somebody's going to ask, can you get concurrency and do some of the calculations during the SPI transfer? How would you do that? There's at least 2 ways. Neither of them easy. Hard way number 1 is to figure out how to draw a ball using DMA. Do the DMA transfer to the SPI channel under hardware control so it can be completely concurrent with the CPU. Hard way number 2 is to rewrite TFT master to include your computational code. Right, that means that you have to compute each ball during the time that the transfer for the ball before it is being sent. That's horrible. But it would work.
I have a question.
Yeah?
Is there a reason you couldn't interleave those 2 things by yielding back and forth between threads?
Ooh, could you possibly rewrite the TFT master as a thread that you could yield during the transfer? That's an interesting idea. That probably would work. That's hard idea number 3. But yes, that would probably work, right? Just to spawn a thread instead of calling the TFT draw routines, spawn a thread to do the draw, and then yield on each transfer. Oh man. That means flattening all of the subroutine calls so that you can do the yield. That's 3 hard ways of doing it. Are any of those worth it? Oh, golly, I doubt it.
Going back, plib does say what you can set the divider to on SPI. It says the baud rate, well, it gives a formula for it. It's FPB over paren 2 times paren SPI BRG plus 1. So you can set it to any
Even. So any even number.
Between 2 and 1024.
Aha, so it's any even number. So 3 doesn't work, but 6 would.
Yeah.
But at 60 megahertz, that still gives you 10 megahertz. 3, 4, 5. So still doesn't work out. You can't go to 80 megahertz. The system does not, you can't overclock it to 80. At least I've never found a chip that runs at 80. Now, if you cool it with dry ice, maybe. Again, that's another hard option I don't think you want to look at. What else? Anything else on lab 3?
For collisions, can we just check to see if any of our drawn pixels are colliding, or should we actually check the radius?
To see if you have overlap of pixels.
So you would recommend drawing balls with those 5 pixels?
Well, this 5 pixels is kind of the 0th approximation for a radius 2 thing. You could draw 1 pixel and set the collision radius to 1.
Can we do a 0th approximation of radius 2 for collisions? Or should we do...
I don't think that'll work because that's rather anisotropic, right? Collisions from some directions have a bigger radius than collisions from other directions if all you're doing is detecting pixels. I think it's better to actually calculate the sums of squares, which is probably faster than reading back the display. Can you read back the display?
I don't think so.
So you'd have to keep an array of bits. Do you have enough memory to keep an array of bits on a 320 by 240? 320 by 240 is 75,000 bits? 75,000 bits. So, or close to that, maybe 72,000. So you need 72,000 bits. You divide that by 8. That's 10 kilobytes. Yeah, you could do it. You could have a bit-packed array of pixels that are turned on and look for overlaps fairly quickly, actually. Could you do it faster than you could just take the square root of sums of squares of 2 numbers? I'm not sure. Because you have to, if you're looking for a collision, you have to look at several points around the thing, right? Of course, if you build a quad tree of locations of the balls, then you wouldn't have to search as much. Oh man. Mostly what I'm interested in here for optimization is avoid floating point, think about the order of operations, get rid of operations you don't actually need, like multiplying by dt. If you choose the units correctly, in this case time is in frames, I'm more interested in that level of optimization than I am in sort of extreme optimization by completely alternate algorithms. Although it's certainly interesting to think about those, and some of them may be much faster. I get surprised every year. First year I did this on AVR, I said you had to do at least 14 balls. And that's an 8-bit machine running at 15 megahertz, okay. and the most I saw was right around 110. So on this architecture, which is about 12 times faster doing arithmetic, but not necessarily faster at drawing points, because the AVR was drawing points to memory. Now we have another graphics system that is in use that we have code for, and that's television as opposed to TFT. It's very fast to write to the television because that whole system is DMA based. So you do a memory write to memory, and the pixel appears on the screen with an effective time of 1 cycle. That piece of code, though, is huge. Okay, what else? Anything else on Lab 3? Let's do a little bit on Lab 4 today. Talked a little bit last time about serial, mostly to kind of get you interested in the idea of looking at the historical nature of these protocols. Most of these protocols have a simple beginning that has been wrapped up in layer after layer of emulation until you can no longer figure out how anything works. I feel that way when I look inside of a car's engine housing. I used to be able to figure out how cars work by looking at them. Now all I see is tubes. You know, so. But one thing I do need to talk about is pulse width modulation, because for this lab you're going to be producing an analog signal as an approximation given by the relative on and off period of a square wave. So a 50% duty cycle square wave of amplitude 3.3 volts has an average voltage of about 1.6 volts or so. And a PWM is a way of producing a variable duty cycle, fixed frequency. So it's variable duty cycle, fixed frequency, hence pulse width modulation, not pulse frequency modulation. Pulse width modulation that averages out to lower values or higher values. So if you're using PWM to approximate an analog value, then the very next step you're going to do after the waveform is a low-pass filter. For this lab, you're going to have to build 2 analog low-pass filters for 2 PWM channels, and the motor itself is a low-pass filter. So the motor itself is going to average out the pulse train to a constant speed as long as the pulse train isn't too high frequency. Why is that? It's because the 4N35 opto isolator we're using has a bandwidth of about 1 kHz and not too low a frequency, because if you get down to a period which is comparable to the motor time constant, it is no longer a low pass. It's not going to low pass filter. You'll get a real jerky, torquey kind of thing. It'll go it'll speed up, slow down, speed up, slow down, speed up, slow down. So you want these pulses to be short compared to the motor time constant, which in our case you can measure it, but it's going to be around a second or so. You take the fan, you spin the blades, you watch them slow down, you say, oh, it takes a couple of seconds to stop. So really what you care about for time constant is 1 over E time, but you're probably estimating 3 E times or so if you're saying it's stopping. So you divide by 3 and you say that's a time constant. Or of course, you plot it on the scope. So there's going to be 3 outputs from the PWM, PWM channel 1 is going to have two outputs. It's going to go to the opto to run the motor, and it's going to go to a low-pass filter and to the scope. Wow. My sequencer is all messed up. To the scope. This is going to allow you to visualize the control parameter. So this is going to be, the output to the motor is how you're controlling it, and you're going to be able to visualize that on the oscilloscope. This is not something you build last because it's required. It's something you build first for debugging. PWM 2 is going to convert the RPM measurement to, so let's rearrange this. Say we're going to take the RPM measurement that you're making with the infrared sensor. You're going to turn it into a PWM signal. You're going to put this out through a low-pass filter to the other channel of the scope. Scope 1, Scope 2, so that you can see what the motor is actually doing. So you might give it a command. You might give it a command. This thing shut itself down. It's back. You might give it a command like this on channel 1. It turns out you can get used to that sound. You can even get used to the sound of dragging your fingernails along the board. I won't do it because I have some sympathy for your feelings. But you can get used to it. You can desensitize yourself to anything. So PWM channel 2 low pass is going to produce the motor response, which might be quite different. And so in response to this signal, you're going to optimize the motor response. So you need the PWM signal, you need the RPM signal, and you need the control signal to debug this. Build it first. Get the two PWM channels working so you can debug this thing in a sensible fashion. You also need these plots for your report. Turns out that, now, any questions on this? Turns out you can that an output compare unit, so these, remember OC3? Remember back in the dim days of Lab 1? Talked about output compare units. Well, you're going to be using them again because they also mediate PWM. And in the case of the output compare units we're going to be using, you take some timer, and in this case it has to be either timer 2 or 3. Timers 4 and 5 can't control the PWM or the output compare units. And timer 1 I'm not sure about. You're going to feed this, you're going to bolt this in hardware to an output compare unit, which then compares the 16-bit value of the timer to 2 separate registers. There's an equality operator that's going to compare with OCXR, and another equality operator which is going to work against OCX RS, where X can take a value from 1 to 5. So there's 5 output compare units. A match on, you can set up a pin, let's say OC3. You can set up a pin, these are on PPS. You could set up a connection between the signal OC3 and a pin using PPS that will toggle a pin high on a OCXR match and toggle it low on an OCXRS match. So the timer is going to tick along at a constant frequency. Tick, tick, tick. And every time the timer ticks, sometime during that cycle, these two equalities are going to take place and you're going to generate a square wave with a variable amount of high time relative to the low time. And the frequency will be fixed because the timer frequency is fixed. So the timer is going to set the period of the PWM, which must be, it must be less than or equal to 1 kHz. It must be less than 1 kHz because that is the bandwidth of the opto-isolator. On the other hand, you want it as high as possible because you want it to be above the cutoff frequency of the fan. And in fact, you've got to put low pass filters on here. So let's say you have this at 1 kilohertz. Let's say you have the PWM at 1 kilohertz. The fan has a time constant of a second, done, fine. Half second, even that's fine. We need a low pass into the scope. So we're going to take the PWM, which has a kilohertz square wave. We're going to put it through a low pass filter into the scope. We want this to be as responsive as possible. In particular, we want the time constant of the low pass filter into the scope to be smaller than the time constant of the motor. Because we want to be able to get the response of the motor on the scope. And to do that, we have to have a time constant which is shorter than the time constant of the motor. So, 10 to the minus 3 seconds. Motor is, about 10 to the 0 seconds, or a little bit smaller than that. So we could pick this time constant to the scope to be something like 10 to the minus 1 seconds, or maybe a little bit smaller than that. So how good is the smoothing? We have a PWM. If we smooth it through an RC circuit, we're going to see little transients corresponding to each of the pulses, which are smoothed out to some extent by the RC circuit. If we were to set the frequency of the PWM to be a kilohertz, the time constant of the low pass filter to be 10 hertz, ratio is about 100 to 1 between the two frequencies. So what is going to be the height of this little residual artifact? What percentage of the output signal is that going to be? The frequency is 100 times the cutoff frequency. The slope of the cutoff of an RC filter is -1 on a log plot. So you'd expect that the residual noise that should appear on a waveform should be about 1%. That's pretty good. That's good enough. That's good enough for a lab write-up for sure. Because the resolution of our scopes is only about 1%. About 7 bits. So setting this to 100 hertz, you say, oh, if the maximum frequency is a kilohertz, maybe I should drop this to 100 hertz. Now the now the ratio between the PWM and the scope low-pass filter is only 10 to 1. Now the residual noise is going to be more like 10%, and that makes understanding the waveform fairly hard. So what I'm going to suggest is set the PWM to kilohertz, set the time constant of the scope to something like 6 radians a second, or 5 radians a second, or 1 radian a second. And 6 radians a second. And then the motor will be slower than either of those, and so all of the time constraints are met. Luckily, it's fairly easy to do a PWM setup, and I thoughtfully gave you an example on the ProtoThreads page. In the 1.2 section, there's an output compare unit example. Aha! And one of them is a PWM running on pin 18. So let's take a look at that for just a minute. It's very simple to set up. The user interface here sets the PWM on time with one call. We're gonna input, the human is going to input this. I use this for testing. The human is going to input this value, and then you say set DCOC3 PWM to PWM on time, and it works. So we're setting the on time. What is the total time? The total time? Well, let's say you're clocking the clock. Let's say you're ticking the timer at 40 megahertz. You have a PWM period of 1 kilohertz. How many ticks of the clock? 40,000 ticks. So this PWM on time is going to be scaled to 0 to 40,000. At 0, the motor will be stopped because there is no output. And at 40,000, it will be on all of the time for full speed. So the scale of the PWM on time is determined by the on time is scaled to 40,000. So to get this thing going 3,000 RPM, which is full speed, 3,000 RPM, you've got to set the output to 40,000. To make it go 0, you've got to set it to 0. Sounds like a fairly easy linear relationship. So the only other thing we need to do is to set up the PWM. In this case, I was running it off of timer 2. So we're going to set up timer 2 to some generate period. It's going to sit there. That'll be the PWM period. In this case, probably 40,000 or so. And then we're going to open OC3 using timer 2 as the source. And we're going to set it in PWM fault mode disable. Because so many people run motors off of PWM channels, and because a motor failure can cause real damage in the real world, it's nice to know if there was a failure on that channel, and this will tell you that, but we're turning it off because we're good at what we do. No, we're turning it off because the motor is a fractional horsepower motor, and it doesn't matter even if you stick your finger into it. Don't try that though. So then you give it PWM time, on time, as an initial first time. You might set those both to 0 to initialize. That way the motor would be turned off. Or if you don't want the motor to be at 0 speed when you boot the system, you might set it to some finite speed like half speed. So half speed here would be what PWM on time? 20,000. About half of the 40,000 period. This particular code also sets up another output compare channel, OC2, but this is not in PWM mode. OC3 is in PWM mode, which is what you're going to want to use for Lab 4. So you turn it on, and then at any time in the code, you merely give it a new on time, and the speed of the motor will change. So what you're going to be doing is your speed control algorithm is going to be calculating what the PW on time should be to make the motor go the speed that you want. So you type in 1000, S equals 1000 on the command line, and the system should apply the correct voltage to bring the RPM up to 1000 RPM. Now you're going to have feedback. You're going to have a sensor running that can measure the speed. And we have to talk a little bit about control algorithms, which we'll do in the next lecture. But the basic operation is you're going to run some algorithm which determines what the setup, the PW on time should be to make the motor go the speed you want. So this is quite an easy peripheral to use. Setup time is minimal, setup complexity is minimal. You can run 5 PWM channels independently because there's 5 output compares. So in particular then for this lab, running 2 is not a problem. Pick any 2 of the output compare channels, run them off the same timer, and you've got your outputs. So the resolution of the PWM, how closely can you set it? The resolution is determined by the period of the timer. So you can set, for a 1 kilohertz PWM rate, you can set this to 1 part in 40,000. If you sped it up to 10 kilohertz, you'd only have 1 part in 4,000. 1 part in 40,000 is way more than you need for this lab, but that's what you have, because you have to have a rate of less than a kilohertz. And what will be the symptom? You have an opto. What will be the symptom if the PWM is too high frequency? Remember, this is the opto circuit here. Well, the first answer is you look at it on the oscilloscope and it's not a kilohertz, right? But a lot of people don't like to do that. They prefer to debug the hard way by hooking up circuitry. So what will be the symptom if you say set this frequency to 10 kilohertz? What will happen? It's a little hard to say, but if the duty cycle were around 50%, and this transistor can neither cut off nor turn on completely, then the voltage here is going to be somewhere near the gate voltage, and you're going to get some output which you cannot control very linearly, if at all. Because you're going to be right in the turn-on region of all of the transistors. Oh, yeah, let's talk for a minute. We have just about a minute. That's what it'll take. This resistor, how big should it be? Who's actually read the lab? It turns out that the reason this is here is that photons from the photodiode inject charge carriers into the base, turn on the transistor so that it conducts. When you turn out the LED, how do you get rid of those charge carriers? How do you get rid of the charges? If you've now reverse biased the base emitter junction, it's a really good insulator. And so you can't get electrons off of here, you can't get charge carriers off of here if you don't have this resistor. It'll just sit there and stay turned on forever once you turn it on. Or actually, it's not forever, it has a time constant of like 3 seconds. So you have to have a small enough resistor to get rid of the charge at a kilohertz rate. But if you make it too small, you can never turn the transistor on because you can't generate enough photocurrent. So the photocurrent multiplied by this resistance is going to have to be at least 0.7 volts. So I'm suggesting you start with a megohm. But if it's too slow, make it smaller. If it doesn't turn on, make it bigger. Okay, let's go to the lab. And Monday afternoon, 3 to 6, lab is open. Tuesday, 10 to 4:30, lab is open. Wednesday morning, lab is open. Wednesday lecture, lab is open. I don't want to hear anybody complain about not enough lab time.